and thank you very much for joining me. My name is Louise, and today's lesson is about Newton's laws of motion. So, anyone interested in physics, or anyone even just interested in moving, Newton's laws of motion are all about how we move. They govern how everything in the universe moves, be that humans, planets, animals, plants, everything is governed by Newton's laws of motion, which is pretty amazing. So, first of all, who was Sir Isaac Newton? I'm sure you've heard his name before. If you haven't, don't worry, this will be the first time of many. But Isaac Newton was born in 1643 and became very famous for his work on gravity and his three laws of motion. So you might have heard of him because he's known for being the man who discovered gravity. I say discovered like this because obviously gravity was already there, it was always there. He's just the one who understood it and explained it to the world. He's also well known for his work on light and colour and what is now called calculus, which is a branch of mathematics. So in his life, he did lots for the world of science. The famous story of an apple falling to the ground from a tree and then Newton having a kind of eureka moment and thinking, there must be a force which makes that happen. That's gravity. Illustrates how Newton's work was inspired by things he observed in the world around him. So he was very much a practical scientist. He would see something happen and he would want to explain it. In many respects, he can be viewed as the greatest physicist of all time. There were lots of predecessors of note, Archimedes, Galileo, but it was Newton who really exemplified the method of scientific inquiry that would be adopted throughout the ages. So, seeing something happen, thinking, I want to understand how that happens, and then doing rigorous experiments to understand it. For nearly a century, Aristotle's description of the physical universe had proven to be inadequate to describe the nature of movement. Newton then came along, tackled the problem, and came up with three general rules about movement, which he published in his most famous work called Principia in 1687. So, what are these laws of motion? They're not very creatively named, these three laws of motion. They're called Newton's first law, Newton's second law, and Newton's third law. But at least you don't have anything super difficult to remember. First, second, third. And these laws of motion help us to understand how objects behave when they're standing still, when they're moving, and when a force acts upon them. So in all situations, they help us to understand how an object will move. These are the three laws of motion, and each law Newton developed has significant mathematical and physical interpretations that we need to understand motion in our universe. They apply in all situations, wherever you are and whatever you're doing. Even if you were lucky enough to go to the moon, Newton's laws of motion will apply to you on the moon. It's pretty incredible. So let's go through them. Newton's first law of motion. This is sometimes also called the law of inertia, inertia being lack of movement. So in the Principia, the Newton's published book, word for word, it says, every body continues in its state of rest, or if uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it. Obviously, Newton wrote that a long time ago. It's not super accessible language, but basically it's making 2 points. First of all, an object that is not moving will not move until a force acts upon it. So an object at rest will remain at rest until a force acts upon it. This is kind of saying objects act predictably. If there's a football sat on the ground, I don't expect it to start moving unless I go up to it and kick it. So some of these laws are putting into words things that we've all seen in our day-to-day lives and we all kind of instinctively might understand, but Newton made it scientifically applicable. So that's the first point. An object at rest will remain at rest unless acted on by a force. Number 2, an object that is in motion will not change velocity. Velocity is the scientific word for speed. Will not change velocity or stop until a force acts upon it. So that's to say, if I were to throw a ball and no other forces were to act upon it, it would never stop. It would keep going forever. Okay, same if you were to kick a football and no other forces acted upon it, it would keep moving forever. But I'm sure now you're wondering, but Louise, whenever I throw a ball or I kick a ball, it does stop. So why does it stop if you're telling me that if there's no force acting upon it, it won't stop? That's because there is a force acting upon it, and that force is friction, or if it's going through the air resistance, which is a type of friction. So, frictional force always happens in the direction that is opposite to movement. So, if I'm moving this way, there is actually air resistance happening against my hand this way, the opposite direction. So we can see it in this diagram. We've got a block on a table. Block is trying to move this way because it's got a pushing force pushing it this way. The friction from its contact with the table is trying to push it back. It's trying to stop it from moving. So when we go back to our law, an object at rest will remain at rest unless acted on by an unbalanced force. We are being acted on by forces when we, for example, slide a book across the table. Although it might not seem like anything we can see, there's no one physically pushing it back, but the friction from the table is pushing it back, so there is a force acting on it. So it's important, this law is quite easy to remember if you think of the law of inertia, that basically whatever's happening, the status quo, will not change unless there is a force acting. But we have to remember friction and air resistance, forces that we don't necessarily see as much. We're not seeing a physical push, but it's there and we have to remember it. Okay, so that's the first law. Moving on to Newton's second law of motion. Again, I'll read you the exact quote from Newton's published work and then I'll make it make sense. So it says, the acceleration produced by a particular force acting on a body is directly proportional to the magnitude of the force and inversely proportional to the mass of the body. Okay, that's super difficult to understand, but basically what it's saying is when a force acts upon an object, it will cause the object to accelerate. The bigger the force is, the bigger the acceleration. So I have a glass of water here. If I were to lightly push it, it might slowly fall. So it has a slow acceleration. If I pushed it really heavy, it would fall over much quicker. So the bigger the force, the bigger the acceleration. The other thing to think about is mass. The larger the mass of an object, mass being the word we use in physics for how heavy something is, the larger the mass of the object, the greater the force will be needed to cause it to accelerate, to cause it to move. So this glass of water, which is virtually empty, it's lighter now, so I don't need as much force to tip it over. If it were full of water, it would be heavier. I would need more force to tip it over. So that's what it means when it's saying proportional and inversely proportional. They're very complex ways of saying proportional means if you increase force, you increase acceleration. Inversely proportional means if you increase mass, you decrease acceleration. So that's what it's saying. And with lots of things in physics, we can put them into nice, handy formulas, like you can see here. Force equals mass times acceleration. You will definitely do this in physics when you get there, so this is just a heads up for you. So this law, another way to state the second law is to say it takes more force to move a heavy object than it does to move a light object. You try and rationalise this law, understand this law in your head however you want to with the ways that I've said it. There's lots of different ways of understanding it. It's quite easy to think about, and especially if we look at our diagram here, to say that it takes more force to move a heavier object than it does to move a light object. We can see the man really struggling with the 400 kilogram mass. He's having to push a lot of force there, a lot of effort. Compared to the 40 kilo mass, it doesn't look too difficult. He's not using too much force. The law also explains deceleration, or also known as slowing down. So we can kind of think of deceleration as acceleration but with a negative sign before it. So for example, a ball rolling down a hill moves faster, it accelerates because gravity is the force acting on it and pulling it down. If the ball were to be trying to roll up the hill, it would slow down, it would decelerate because gravity is pulling it back down. So that's the force acting on it there, is gravity. So that's the other thing we have to remember when we're thinking about these laws of motion, that there are lots of different forces at play. Friction, air resistance, our pushing and pulling forces. There's also gravity going on, lots of different forces which might act. We're just going to have a look at some worked examples to try and use this formula that we've got from Isaac Newton and see if we can put it into practice. So let's have a look. The first thing to mention, when we see a force, the unit we use for force, so for example, the unit of mass is a kilogram, so this weight in the middle is 5 kilograms. The unit of force is a big N, and that stands for, if maybe you can guess it, Newton. So we measure force in newtons after Isaac Newton. So here's our example. K is pushing a box along the floor and the box has a constant velocity and she's pushing it with a force of 20 newtons. The mass of the box is 5 kilograms. What must the frictional force be? So when we're looking about the second law, we have to remember that forces are acting in both ways. So we've got K's pushing force happening this way of 20 newtons, and we've also got friction happening this way. We need to find out the resultant force, which means the force when you take away the friction from K's pushing force. That's the total force we have left going in this direction. So this box is going at a constant velocity. Constant velocity means it's not accelerating. It is not getting any faster. If anyone is super switched on, super awake this morning, you might have realised that that means the friction force must be the same as the pushing force. It must be 20 newtons as well, because the box is not accelerating, so we must have 0 overall force acting on it. Because remember, when there is a force acting on it, we must have an acceleration. Here, there's no acceleration, so there must be no force acting upon it. Don't worry if you're not quite there with me on that. That's pretty advanced stuff. We're getting really close to GCSE level things now, so don't worry. We're going to have a look at another example. What happens if the force is increased to 30 newtons? So K's pushing force is now 30. The friction force back is now 20. What acceleration will we get of this box? So again, as I said, we need to find the resultant or the net force. So that's the forward force, 30 newtons, minus the backwards force, 20 newtons. So we have a resultant force of 10 newtons going forwards. Now, we have the force, we have our mass, 5 kilograms. How do I get my acceleration? So we have this formula, force equals mass times acceleration. Or, if you've done any formulas before, you will know that we can rearrange formulas to get the thing that we are missing. So we have force and we have mass, so we want them on the same side of our equation, of our equals sign. So what we're going to do, we're going to bring the mass under here, under the force, to make it acceleration equals force divided by mass. So then acceleration equals our force of 10 divided by our mass of 5, which gives us an acceleration of 2 meters per second squared. Again, that's super advanced. Don't worry if you haven't done any rearranging formulas or anything, that's quite a lot, but I just wanted to show you how we go about using these formulas which Newton gave us. Okay, on to the third law of motion. This law in Newton's work said, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. What? That's Very difficult English there, don't worry. What it's saying is whenever two objects interact, they exert equal and opposite forces on each other. This is sometimes restated as every action has an equal opposite reaction. This is the one that is always really the most difficult to get your head around, so don't worry, just stay with me as best you can. So it's important to remember for this law that for it to apply, the object must be the forces must be acting on each other, so through the same object, and they must be of the same type. So they must both be, for example, contact forces or pushing forces. We can't have one force being air resistance and one force being contact. Okay, they have to be the same type of force. What this basically means is that when you're pushing on an object, that object is actually pushing back at you. Otherwise, if I push an object, my hand would just go straight through it. The object is pushing back at me. For example, as well, when we're standing on the ground, you're pushing down on Earth. Earth is pushing back at you, because if not, you would just fall straight through the centre of the Earth. Okay? So these are two forces resulting from the interaction. The forces are called the action and the reaction forces. Same, if you're watching this, you're probably sat on a chair. Me too. I am pushing down on this chair. This chair is pushing back up at me to keep me up. Yeah? So the same, if a cat sits on the ground, there are contact gravitational forces between the Earth and the cat. So gravity, every object with mass has its own gravitational pull. So a cat sat on the Earth is using its gravity to pull the Earth towards it. The Earth is also using its gravity to pull the cat towards it. The forces are equal in size and opposite in direction. This, like I say, is a little bit difficult to get your head around. For example, if I'm pushing on the Earth as much as it's pushing on me, why are neither of us moving? Why aren't I moving if the Earth is really pushing me? And it's because the Earth is so much bigger than me, it has a much greater mass, I can't push and move the Earth. The forces are perfectly balanced, there's no net force, there's no resultant force because they equal each other, so then there's no movement. Because we know as well from the first law that we need a force acting to make movement. Okay? A helpful example, the one that I find kind of the most illustrative for this law, is the example of flying birds. So birds flying gracefully through the air depend on Newton's third law of motion to do this. As the birds push down on the air with their wings, the air is pushing their wings back up and keeping them in the air. It's giving them lift. So the wings of a bird push air downwards. In turn, the air reacts by pushing the bird upwards. The size of the force on the air equals the size of the force on the bird. The direction of the force on the air is down, is opposite to the direction of the force on the bird, up. So this action-reaction force pairs make it possible for birds to stay in the air and fly because the air is pushing them up. Okay? So that was our quick introduction to Newton's 3 laws of motion. I hope you've been able to stick with me and understand. Honestly, I still struggle understanding the third one sometimes. I'll think I understand it and then I'll find a new example and I'll think, I can't figure out how that works. So don't worry. Try and get your head around the first and second. Keep trying with the third. Read some other examples and that will definitely help. So thank you very much for joining me today and I hope I will see you in my other videos. Thank you. Bye.